the team don't have the
I think.
Can we start it too, or?
Yeah.
Okay, great.
Okay, guys. When you're ready, you can start the meeting. This is not the first time do you have the video readiness review, right?
No, it's not. It's actually our fourth video safety review.
Okay, and do you have any question about the process of the review?
Yes, in general, we noticed that every judge wants to see something different. So I'd like to ask you how you would like to see the proceeding, or what would you like to see in particular?
Okay, I see that you have a presentation ready. We can start with that, and then we can pass with the rocket. I would like to see the rocket. We can start with subsystems like the aerostructure, recovery, avionics, and the other ones. But I can make a few questions, and you can answer, respond that.
Great. So our idea is this is the presentation, and this is how we imagined that the meeting will go. First, we'll do a general overview of the rocket, just show it to you on camera, and show you the drawings, the general drawings, and then do a detailed review from aft to forward end with the presentation as a visual aid, and showing the physical components and explaining them in detail. That's how we imagined it.
Okay.
Great. So, no, is Patricio in the call?
Yes, I am.
Great. Hi, Patricio. How are you? This is Walter, and you already know Brett.
Hi all.
Hi, Patricia.
So I am the advisor for this team. So I'll just be sitting here and listening.
Okay, nice to meet you.
You too, Walter. Hope to see you soon.
Yeah, perfect.
So, hi, Walter. Nice to meet you. This is team 207 from Buenos Aires. I'm the operator, the team lead, Felipe Rautel.
You're echoing. Can you turn off all?
Guys. Okay.
You have echo.
We're going to turn it on from here. How does it look now?
Yeah, better. Yeah.
Better?
Yeah.
Great. Let's start from the top. So, we are Team 207, Instituto Tecnológico de Buenos Aires. We are building Project Aconcagua, and Lucas Freire, the team leader. Felipe Rautel, from here, is the co-lead. Then Ivan Marcenyuk is the avionics first lead. Valentin Neme is the aerodynamics co-lead. Tomás Mancela, also aerodynamics co-lead. Tomás Proveto, composites lead. Marco Beretta, payload lead. Then Santiago Ponte, recovery lead. And Tomás Wickham is the avionics from the electronic part lead. So right now we're going to show you Project Aconcagua. We've been developing it since August. And let's start with the presentation. We prepared some slides to help guide the presentation. So the proceeding will be the next one. First, we're going to do a top-level overview of the rocket, and then we're going to start detailing each section in detail. So for the general overview,
Si quieren, apaguen esa cámara.
this is a drawing of the rocket. You can see on the forward end, the nose tip, then the nose cone. This integrates the first part of the rocket, the first biggest single part, and we've got another two sections of the rocket that are the upper airframe and the fin cannon. And our rocket has 5 main subsystems. First, the telemetry bay that can be found in the nose cone. Then the recovery bay, also with the nose cone. Then the avionics bay, then the upper airframe, the payload bay. It is the recovery bay and the payload, and then the propulsion subsystem that is the fin cannon. Also with fins and the bow tail. And we have on the bottom part a chart with the main properties of our rocket. So let's show you a visual of the top overview. You can see there the nose tip, the telemetry bay, the nose cone with a sliding field joint, then the recovery bay and the payload attached. And this is our functioning payload, which is disassembled to show it to you properly. And then moving to the aft end, there we have the bulkheads between the upper airframe and the fin can. We have 2 fin cans that are joined by an internal and an external layer of fiber, glass fiber on the inner side and carbon fiber on the outer side. And then we have the fins and the centering. The fins are still to be cut from this carbon plate we manufactured ourselves and are going to be joined to the fuselage through this aluminum mounting devices. So let's move on with the detailed revision of every subsystem, starting by the forward end. Next slide, please. So you can see there the general structure. We're going to start off with the nose cone.
The nose cone avionics.
Great. So first we'll go Ivan and Tomas.
So, as Lucas said, this year we were going to have 2 bays. This one is to have telemetry, so we want to receive data out of this one. And talking about the structure, we have a positioning ring where we can bolt this plate to it so that it gets fixed.
And talking about the electronics, we have several boards that are in charge of data acquisition and telemetry. COTS board is a Telemega 5th version board. This one acquires GPS position, altitude, velocity, acceleration, and sends the data with this antenna to our ground station. We also have our own strata boards. This one has the same capabilities as a Telemega, but it's not in charge of higher charges deployed. It's just for data acquisition and telemetry. And on the other plate, we have a mounted live camera. It's not populated because we are working on it, but you can see the structure. Here should be the FPP camera.
Great, and you can see it on the screen in the presentation.
On the top right, you can see the assembly out of the CAD files. Can you hear it properly?
Yeah.
Great.
Can I see
So-
more close the the nose tip and the
Yes, of course.
avionics. Okay, and the hard point. Can you tell me more about the material about the hard point of the parachute in the U-bolt?
Of the U. Okay, so this is a steel U-bolt. It's a 3/8 inch by 1.5 diameter. The load path in this case doesn't travel through the 3D printed structure, but instead we have kind of a fail-safe mechanism. As when tension travels through here, it goes to the two posts of the U-bolt, and then on a first instance, the load is transferred. If you can see inside the nose cone, we have an epoxy joint glue. Yeah, it's an aluminum like bulkhead glued in the top of the nose cone. And apart from that, we have two bars that you can see here that are made of 6061 aluminum that are joined by this Delrin coupler in the top to an old thread that retains the nose tip that will sit on the fuselage upon this ledge here.
Okay. Okay,
So we
perfect.
have
Thank you.
fail-safe mechanism.
Okay.
Okay. Do you want to continue moving down the fuselage?
Yeah, just one more detail. The avionics bay will be turned on through these switches. These are Allen switches that can be just turned on and off through a 1/4 inch rotation. And the nose cone will feature holes aligned with these switches, so we can turn it on and off.
Okay, I just to confirm that avionics is only for the GPS, or do you
Yes.
activate any paritonics?
No,
Okay.
this is just a telemetry bay. It just works to recover data, send it to ground, and to test the SRAT plate.
Okay, perfect.
Oh, and we've got another detail. The nose cone can be unscrewed so that we can recover data through these holes.
Which will house a USB plug.
So we can do a quick data gathering after the flight.
Okay. Okay, perfect.
Great. So moving aft, here you can see the upper airframe. There it is. So doing a quick presentation of the upper airframe. We have the bulkheads. We have a pair of Radex bulkheads that join the nose cone with the upper airframe. The sliding field joint, and it gets inserted into the nose cone and is fixed during flight through 4 shear pins that are cut at apogee. And then inside of the upper airframe, we've got the recovery bay and the payload that will be presented now again by Ivan and Tomas, and then by Marco, the payload. So please.
I think we lost you guys. There is bad connection. Hi guys, we can see you from the second camera, but we can't hear you.
Yeah, I can hear you too.
Yeah, let's see if they realize. Hey.
Are you able to hear us now? Yellow. Okay, we will continue with the audio from this computer, and continue showing the rocket on the phone. If that's okay.
So, Ivan and Tomas, can you tell us how the recovery bay is turned on?
Okay. So, so these RRC3 have their own cables, bridges connectors, these molex connectors. So
Tommy,
Yeah.
estás mostrando la otra cámara. Esa cámara está frisada.
Okay.
Es esa. Ahí va.
Gracias.
Sorry for the Spanish. It was a quick instruction for the camera.
okay,
Yeah.
so I go again. So you can see in the image that is showing the computer, and here, these boards have their own redundant systems, and the connections are through these connectors. These molex connectors are the female version of it. So we have the male connected to the switches that are downwards, pasted or fixed to the fuselage.
Okay, guys, before we can continue, you can remove the background filter,
Yes.
because when I can see. Oh,
Yeah, that's it. Great. So
yeah, perfect.
you can see in the right images what Tommy just described, the switches that are glued to the upper airframe and contain the Allen switches, as can be seen where I'm pointing at with the mouse.
Okay.
So the procedure will be grabbing the connector that is on the switches, connected to this bay, fix the connection, and attach it to ensure that in all the flight is not moved. And that's it. Then you can mount the bay.
Great. Yes.
Okay, I will. This is the other one. Yes. I will proceed to show you the recovery load path for the U-boat when deployment occurs. So, as you can see, we have this plate right here with a 1/2-inch U-bolt, which is, we have FEM validated this. So this sandwiches between the two bulkheads that you can see. Probably. Yeah. Yep. So you can see our bulkhead right there. That's 2 halves of the radius joint, and we have a gap for the plate here. I don't know if you can see it because my finger is quite tight. We can disassemble it if you want to see it further, Walter. We have a section view also to show you
How the plate is sandwiched. This one on the top right image. That's
Okay.
when it's recovery plate mounting. This one.
Okay.
And this is also a section view of the radix joints. So you can see how the bolts can be inserted at an angle.
Okay. How many bolts and which size do you choose for this mechanical ensemble?
Yeah, we have 6 M6 bolts, and we have FEM validated this joint.
Okay.
Going back to the recovery load transfer with the nose tip. Oh, great.
We have already.
So let's move on to the line diagram. Now Santiago is going to present you the recovery gear.
So I'll explain from the presentation, then I move on to the physical line diagram so we can understand it better. We have two diagrams. First, at flight, that is the first diagram presented. Then when we detect apogee with the two redundant RRC-C3 computers, we trigger Raptor CO2 devices and get the decoupling of this system. We have a drogue and main parachute system. The drogue is a 1.65 feet elliptical canopy of 2.2 drag coefficient, which ensures us a 30 meters per second descent rate at the opening of the main parachute. This drogue parachute is connected through a 10-foot Kevlar shock cord to a quick link, swivel link, and then 3-ring device system. The swivel link prevents us from entangling the shock cords, and the 3-ring device is used to assure further deployment of the main parachute. So once we reach 1,200 feet above ground level, we trigger two redundant line cutters to release the 3-ring device system. And now the tension, I will come back. And now the tension travels through this 5-foot Kevlar shock cord and extract the main parachute from its pod, which is the parachute opening device. Once this bag has been extracted, the main parachute will begin its inflating sequence and will start to progressively cut some shear zip ties that we will place in its 10-foot shock cord to reduce a little of the energy when the main parachute inflates. So now we have main parachute descent, which is, I forgot to mention this, it is an 8-foot elliptical canopy of 2.2 drag coefficient, which ensures us a 6.9 meters per second descent rate until landing. So now we have the main parachute through a 10-foot, through a 10-foot Kevlar shock cord, and then we have the nose cone, which is attached to its U-bolt through a 20-foot Kevlar shock cord. This 20-foot length, prevents the nose cone from hitting the rocket body's fuselage at main parachute descent. And then on the other side, we have another 20-foot shock cord, which will remain the drogue parachute and the pod and the remaining parts of the recovery sequence. So nothing gets lost at descent. We'll show you a bit of the line diagram, of the physical line diagram.
You already tried this configuration in a flight, or is a conceptual design?
No, it was used the previous years, and we work very tightly with a business here in Argentina that specializes in recovery, and we're working with him and came up to this diagram as improvement of last year's version, but it's very similar.
Okay, perfect.
It's already been tested.
I have a question about this. Could you go back to the previous slide?
Yes.
So
Yeah.
During drogue descent,
Yeah.
the drogue will be directly above the compartment that has the main. So as the main comes out and it starts to unfurl, how do you prevent it from tangling with the drogue?
Yeah, so we have been talking about this with our parachute specialist. He ensures us that when the main parachute inflates, now the drogue has not enough airflow to keep inflated, so it falls as a separate bag next to the fuselage of the rocket body.
And just to prove the concept, we're going to test it. We're going to test the complete recovery sequence via an ongoing car, a car with almost the velocity of the main descent. We're going to unfold the main when the drogue is open and just check that it doesn't tangle.
Is the main in a bag or is it in a compartment? I can't tell from this diagram. It looks square. How is it prepared? Is it folded, wrapped? What are you doing with it?
Yeah, so the main parachute will be kept inside the pod, a semi-cylindrical pod, which will come out when we trigger the line cutters and release the 3-ring device system. So the 10-foot shock cord and the main will be kept inside a semi-cylindrical pod, and the drop parachute will be enveloped inside a small fabric, small piece of fabric.
But the pod is a bag.
Yeah. Sorry, the pod is a bag.
And the bag is extracted via the drogue parachute. So when we detonate the line cutter and release the 3-ring, we will cause tension upon that 5 feet line, which extracts the bag and drives the drogue parachute further than the main opening. That's why our partner with IREC, which is the one that manufactures our parachutes, said that we wouldn't have entanglement.
Is the bag connected to the top of the main, or is it only connected through that cord that I see on the right side of the diagram? It looks like it pulls it out.
The one that says nose cone, or which line in the diagram?
So can you just show me how the cords connect to the bag and how the main, if it connects to the bag, connects? Sometimes when you fly with bags, you attach a line which is inside the bag to the top of the canopy. I don't know if you're doing that. So could you show us the actual materials on the table there and how they'll be packed?
Yeah, I have a picture. I don't know if you can see properly. I have a picture of the bag. It will seem like this. So it's a fabric.
Yeah. It's impossible to see the picture.
Yeah, but do you have like physical components?
Yeah. Can't you show us the bag and show us the main? How will it be connected?
Yes, currently we're expecting the main to arrive, but we can tell you that it is going to be joined from the inside. The pod is connected to the top of the parachute through a line.
Yeah.
Yes, we are doing that. We just can't show it to you yet because we're waiting on the arrival of the parachute yet. But if you want next week, we can show it to you. But yeah, it is going to be connected through an internal cord.
Sorry, I think the guys forgot to mention this, but in the table is what we have from, I believe, last year rocket, because we haven't received the parachutes for this year yet. So that's in the table is the system from last year, which is as Lucas explained, very similar to what they are going to use this year. Just that small comment.
Okay.
Yes, thank you.
Could you go to the next slide?
Yes.
So in this diagram, where is the bag?
The bag is
Actually
has already been extracted and is connected through this 20-foot shock cord and its 5-foot shock cord.
Okay, so the bag is small square where the curtain
sorry,
was.
I just noticed this image contradicts what I just told you, but it's just waiting to be refreshed. We have another version of this drawing. We have to insert it yet, but the main shoot back would be
linked to this end of the parachute.
Okay.
So that cord, which you show with the drogue hanging down, will actually be above the main, right? Because the bag is above the main too, right?
Yeah, at first, yes.
Yeah. Do you need to update the diagram and send us the final configuration, because we need to review that?
Yes.
The object is to prevent that you have any issues in the recovery.
Yes,
Yeah.
of course. As soon as we end the meeting, we'll send it to you.
Yeah, I'd like to review it when you have the actual components, your parachutes and everything. So independent of Walter's review, I would like to see that when you have all the components from your supplier.
Okay,
Yeah.
great.
Okay.
Great.
Okay.
So I have a concern. I fly with a system like this a lot. The risk sometimes is the main canopy tangles in the components which are above it. So I just want to review very carefully what you propose so that we avoid, potentially a partial inflation of the main.
All right, perfect.
So
Great.
that's all for now. Thank you.
Great. Thank you, Brett. So now we're going to show you you want to show the line diagram?
We can show it when we have the final design,
Yeah.
maybe.
When the components arrive, we can show you a video of the finished recovery system. Okay?
Yeah. Yeah, that's fine.
Yeah.
If you have it, you can add
drogue
the recovery system packing
Sorry.
sequence.
You both talked at the same time. I couldn't hear you.
Sorry. If you have it, you can add the recovery system packing sequence.
Oh, you want to see the recovery packing sequence?
No, if you have a
Yes, we do
document
have.
that you can add or send us with the video.
Yes,
Okay, perfect.
yes, we do. We have it we have arranged it with our manufacturer. We already have it, so we'll be sending it to you.
Okay.
So do you have the actual drogue parachute you plan to fly with, or are you waiting for the supplier?
We're waiting for it to arrive from the supplier, but it's already it's already almost done with the manufacturer. It should
Okay.
arrive this week.
Okay. Do you have the actual shock cord you plan to fly with, or are you
Yeah.
waiting for that?
We have everything except we have everything part of the recovery gear. We have the shock cords, the swivel links, the quick links. We're just missing the parachutes and the 3-ring that is supplied by this business aero rigging in Argentina.
Could you please show
Yeah.
the recovery harness and quick links and so forth that you'll attach to the bottom part of the rocket? Can you show us the actual links, the cord, the knots you'll tie? Let's look at that.
Of course.
All right. So here we have the physical line diagram. As I was saying, we have a 10-foot shock cord for the drogue, which is a Kevlar shock cord rated at 5,300 pounds, which gives us a safety factor of 4 for the partial opening. Then we have some quick links and the swivel link rated at.
Could you please bring the camera very close so we can see the details? Like right again. Yeah.
Yeah, perfect.
The quick links and the swivel link
Okay.
for the shoot, while giving us safety factors of 4.5 for the
Okay.
partial master. And then when the 3-ring, which is illustrated with this bag, gets gets triggered. Now we detach the parachute bag from this 5-foot camera shock cord. They are all rated at the same strength, which is
They are 5,300 pounds rated half-inch camera shock cord, and we don't line up the end of them at the bottom.
Could you show the end that connects to the lower section of the rocket, please?
This for the U-bolt in the rocket.
Could,
Do you hear that? Do you want us to show the U-bolt in the rocket?
no, I'm interested in seeing the actual quick link that will connect to that U-bolt. Show me that part of the recovery harness.
this would be the lower part of the recovery bay. Connected, so this is the 1/2 inch U-bolt.
Yeah.
And
So just a comment. Often I put a swivel at that location because I find that during recovery, the section of the rocket at the bottom with the fins is often twisting a lot during drogue recovery. So you might consider that as a small improvement. I find that the swivel on the main parachute or even the drogue are less important than having one towards the booster. So just a suggestion.
Okay, so you're recommending that we move this swivel, for example, that is from the main parachute directly to the U-bolt connection.
Yeah.
That's what I typically do. I've actually never had a rocket of your size twist around the main. That swivel is not useful typically.
Okay.
Okay.
I don't know, Walter, what your opinion is on this. but-
Yeah, I usually make the same configuration that you use, but I recommend that you add a swivel in that hard point.
Another
Yeah.
swivel? Or just connect
or
just-
move it.
the quick link and connect the swivel directly to the U-bolt, just to be clear.
Yeah.
Yeah, something like that.
Okay.
Okay. Yeah, well noted. Thank you.
So how will you prepare the shock cords before packing? What do you do with it?
it depends, but for example, the shock cord that connects to the main parachute will be packed with shear zip ties, as I have mentioned previously, to receive some of the energy when the main parachute inflates. And then the other shock cords will just be packed with small, elastic bands to get some more compact design.
Yeah, so normally I recommend you Z-fold, maybe 6 inches back and forth, 6 loops, tape on either end, something like that to organize the cords. You're probably going to do that, but many teams don't think about doing that, and it causes tangles from time to time.
Okay, thank you for the recommendation.
Yeah,
Great.
just add these details in the packing sequence, just to confirm that you have the right procedures.
Okay, great. We'll also add it into the integration document.
Okay.
What the guys will do is to do a special knot. I don't remember the name of the knot, but all the shock cord is configured in this knot, which just untangles when some strain is put on the cord, and then they use the zip ties and the tape to absorb the additional shock of the parachute or the opening sequence.
Sounds good.
Great. So any more questions about recovery?
About the descent rate of the velocity, we can start with that.
Okay, great. So the descent velocity was from 30 meters per second at main deployment, and then after.
Yeah, and the main parachute gives us a descent rate of approximately 7 meters per second. Until
Okay,
the-
and which size is the main and rock parachute?
The main parachute is an 8-foot elliptical canopy of 2.2 drag coefficient, and the drop parachute is a 1.65-foot elliptical canopy as well, with 2.2 drag coefficient.
Okay. You know the colors of the parachute of the which parachutes? Is different?
They are pretty similar to last year's parachutes. If you can show it.
Yeah, just I want to know is you have different colors in parachutes. This is in case of the range officer can see the deployment event in the launch.
Yeah.
Okay.
The main and the drogue, it's nice if they're different color.
Yes, they are different color. We've included in the technical report, I think. Last year we also used different colors for the main and drogue, and we're doing it again this year.
Okay, perfect. And just to confirm, do you use CO2 for deployment, right?
Yeah, we are
Um,
using Raptor CO2 deployment mechanisms.
Okay, and what is the size of the cartridge?
Okay, so we are currently undergoing ground testing for the pop tests, but we have calculated that we will need around 35 grams of CO2, and then we have another cartridge of 45 grams of CO2 that deploys half a second later to ensure deployment in case of a DAT or any problem with the canister.
What kind of shear pins? How many? What
We are
kind-
using 4 nylon 440 shear pins.
How many in total?
4.
4? So
Yeah.
4 for each section? Okay,
We only have one deployment section, so
that's right. Okay, sorry.
that's 4.
Do you have vent holes in the recovery compartment?
Yes, we do have vent holes in the recovery compartment.
How
Okay.
many? How big?
We have 3 4-millimeter holes, I believe.
Okay.
And that hole's already in the body and the A-frame, or
Excuse me?
that vent holes are already in the A-frame?
Can you show us the holes in the airframe?
Oh no. Oh, we've also already made the shear pin holes, but we haven't made the pressure relief holes, but they are very similar. So we can show you the shear pins, the holes for the shear pins, and we can tell you that they're going to be exactly like this.
Okay,
Yeah.
but
Or
you
the-
already,
Yes.
but you don't have already the vent holes in the A-frame.
No, we're doing them this week also.
Okay.
So can you explain exactly where you plan to put the vent holes? Can you show us on the airframe where they will be?
Okay. So we need, firstly, we need vent holes in the upper portion to equalize the pressure for the avionics bay telemetry, which we are looking into that to see how many we need in the upper part, but that is sealed by the bulkhead from the recovery bay. So we have done all our tests with this assembled. And then on the lower part, we were planning to add 4 holes to the recovery bay, like equally apart. That would be like every 90 degrees, a 4-millimeter hole toward the upper portion of the recovery bay. Yeah, it would be almost in this section of the airframe.
you can use the cell phone camera to show it.
Yeah, sorry. We forget. It's on this portion of the near the. You can see the bulkhead because it's kind of translucent here. So we would make them near the top, 90 degrees apart, so 4 holes.
Are you guys
Okay.
What's the maximum velocity for your flight?
We reach approximately Mach 1.8.
Yeah, that's approximately 620 meters per second of max speed.
So the vent holes for the avionics will be towards the front of the nose cone, correct?
No,
No.
but not the movement critical avionics, right? So we have talked that all of the avionics on the upper part here are SRAD avionics that are not in charge of the deployment of charges. All of the deployment is achieved by this avionics bay, which is how right here in this portion of the airframe.
How
So we
far down from the shoulder of the nose cone will that compartment be approximately?
The one that deploys the charges.
Yeah. So what I'm trying to ask, the vent holes for your avionics bay, it's best to keep them well out of the disturbance in airflow that comes when you go transonic and supersonic. So you want to be below the nose cone shoulders so you get out of the way of those shock waves. So I just wondered roughly where the vent holes for your avionics bay will be compared to the shoulder of the nose cone.
Okay, yeah, so if I'm showing you this right here, it's going on.
Yeah.
Sorry, the phone. This is our, wait, I'll go like that, whether you can understand this better. This is our nose cone, right?
Yeah.
Here we have parachutes, and then we have the mission critical avionics is housed in this region right here. So the vent holes will go right here, 90 degrees apart.
Yeah. So, as low as you can, because you're kind of close to the nose cone shoulder.
Okay.
All right.
Great.
Okay.
Thank you.
Great. So moving on to the payload. Marco will show you now how this works. Is that okay?
Okay, so we basically we're going to make a payload. It's a scientific experiment. It's a 3 CubeSat and 2 kilograms. So we can meet the requirements. We designed an infusion pump, which is a medical device used for precise delivery flow. And it's pretty simple. It's simple actually. It's mostly a linear actuator with a lead screw that pushes the syringe and then generates flow. And what we're going to do for this experiment is measure the flow that the infusion pump creates between launch and apogee, as there have been some papers written about how not only vibrations, but high accelerations and even changes in external pressure can influence and affect the delivery of flow produced by these systems, such as creating boluses, which are sudden increments in flow rate, or air pockets, which can strongly affect the delivery of these systems. We have 4 batteries over here. We're using 18650 batteries. We're using 4 of them. Then we also designed our own printed circuit board that houses everything. Yeah, it's a pretty nice experiment overall, I'd say.
Yeah, as far as the rule book goes, what is important about this is we have a fully separate actioning mechanism as per rule book.
Yeah.
So that we don't share any switches with critical avionics or any other subsystems of our rocket.
Activation is given through an accelerometer that detects launch for a high acceleration and then starts the experiment.
Okay, and that accelerometer is activated with a battery, right?
Yes.
And that battery, in which time of the assemble process is turned on or is connected with the sensors?
It's turned on with by the switches on the external side of the rocket.
A separate
Okay.
that is only for payload activation.
Okay. Okay.
Okay.
And that payload is attached with the rocket in all the launch and recovery steps.
Yep.
And what is the method that you use to attach the rocket with all the system? Okay.
There, Felipe
So
is.
as you can see here, we have this plate that is captured by the two radix joints approximately at this height in the rocket. Then we have the avionics plate, what you can't see here is that we have 4 aluminum 6061 T6 rods that join these two plates. So this is non-structural, that's 3D print. And then we have another aluminum plate that is directly bolted to the top of the payload bay, which is housed here. The payload is housed here. And then we have a support on the bottom that acts as a rest that prevents the payload from traveling in tension.
You can see the rest here in the right image of the slide. You can see the payload attached to the recovery bay, and then the payload mounting on the bottom of the payload.
Okay. Okay.
Great.
And review set. Okay, we can pass. Well, Britt, do you have other question, or do you have fine with that?
You may have mentioned this, and I might have spaced out. The payload mounting assembly, is that screwed into the airframe, or is that just glued? Explain to me again how that works.
Okay, so the lower portion are you mentioning, or which portion?
Well, let's.
You mean the mounting?
Yeah, the mounting. That's what I'm
The
asking.
mounting, yeah, the mounting is screwed. You see these holes are used to
There's
screw
like 4,
the mounting to
right?
to the radix bulkheads.
So it's screwed through the airframe to the bulkhead, basically.
Yes.
And it goes through the fiberglass as well, or just the
Yes.
aluminum of the radix?
Yes, through the fiberglass also. So here you can see a 3D printed device to make the holes in the airframe, so we can manufacture make the holes so that the bolts can be screwed into the bulkheads through these holes that are marked in the upper airframe.
Could you zoom in so I can see the hole exactly?
The holes aren't made yet, but
Okay,
they are
so that's where the holes will be. I see.
yes. For example, you can see on this spot or more clearly on this spot the hole on the bulkhead. Can you see that?
Yeah. So my essential question is there a screw that goes through the fiberglass and which then connects to that mounting, or is it just to the aluminum of the radix aluminum ring?
Just to the aluminum of the radix joint. It goes. We have the
Yes.
orifice here, and it stops at the radix joint. So we can separate this because we haven't glued it yet.
Okay.
We want to show it to you.
So let me ask the rest of my question. So let's say that you have an unplanned separation during boost, and the rocket comes apart. This is going to flop down at Mach 1.8. Is it possible for the payload, the weight of the payload, to cause the glue joint to the radix connector to fail and this comes out?
No,
No.
because you mean to the nose cone bulkhead, to the top bulkhead, or to the bottom bulkhead?
Either one. I mean, what will happen if you have a a failure at Mach 1.8. Will it be just a glue joint, or do you have any screws?
I think I didn't understand the question. Did you repeat it? You're asking if we have any additional screws that go through the fiberglass into the radix joint, or if it's just glue joints for the airframe, not the payload.
Well, for the latter question, I think you said it's just the glue that holds this in, right?
Yeah.
Okay, so what I'm asking is if for some reason the apogee joint separates or something happens, is it possible that the entire force of the payload could be pressing against just looks like a 10 centimeter glue joint that could come out? I'm just trying to understand.
Oh, okay. No, we dimension
There's
our
a risk.
glue joints, and every one of them has a safety factor over 6. It's a really, really big area, and we did lab shear test through ASTM mechanical testing, and we dimensioned every joint to have a safety factor of at least 6, even at the worst case scenario. So we rely heavily on our testing. We did many samples, and that's what gives us confidence in our glue joints. So 2 kilograms is a really, really small force for what our joints can withstand.
Have you done a destructive test on a sample? Have you ever actually tried it?
We did ASTM D5686 testing. We did over 70 tests of destructive tests with a universal testing machine, and yes, we obtained statistical results.
So in pounds, how strong is it, do you think? I mean, like 4,000 pounds, 8,000?
Let us look for a calculator.
Yes.
Let it to you in Newton.
Okay.
Or mega.
Walter, that was my only question.
I can tell you that the joint can withstand up to 11 megapascals. That's how many pounds is that?
I just done the math. So the joints can withstand 1,600 pounds per square inch. And the resulting stress, as Lucas mentioned, is 1/6 of that in the rocket.
Great, thank you, Patricio.
So,
Okay.
so for example, if the shock cord was pulling with a main parachute or something, your shock cord, I think you said, was like 3,000 pound strength. So would the shock cord break first, or would the radix joint glue break first? Which would break first?
The shock cord will break first, because the resistance Patricio mentioned is per glued square inch, and we have far more than a square inch of glue joint. So the shock cord would break before the radix joint.
Okay,
That's right.
I understand. Thank you.
No problem.
Okay.
Thank you, Christian, Brad.
We can see inside the body tubes. You can separate the body tubes, and we can see the inside.
Yes, of course. Do you want to see the radix joints?
Show
Yeah.
them all.
Great.
Open everything up. Show each one.
Great. We're very excited about these joints. They were machined on 5-axis in a 5-axis CNC machine, and they are weight optimized and validated through FEM analysis in ANSYS. We also made a loads program so we could estimate the forces on each bulkhead, and that's the input we used to validate it through FEM. So we used a paper indicated that we followed through ESRA links and arrived to this paper to calculate the forces on all of the rockets. So we considered not just compressive and inertial forces, but also bending and wind shear. So Felipe is now showing you the internal part of the rocket.
Okay, so can you hear me properly?
Yeah.
Okay, so our Redex joints have not been glued yet. We're going to get around.
Could you guys stop the presentation and allow us to have this picture be bigger?
Yeah.
Much better. Thank you.
So this is our bottom Redex joint. It's also the motor bulkhead. As you can see, we can separate it for you if you want. This has 3 spokes. Oh, sorry, a little number. 3 spokes and the motor receptacle here, and a 3/8 bolt that goes to the top of the motor as per manufacturer specifications. And this goes like this in the airport, right? This is a beauty joint that holds the thin can, the thin can bay, and the upper part is the upper part of the payload bed, right? So when we separate it via this 6 and 6 Allen head screws, we can separate the two parts of the rocket. And then my partners here will bring up the
So
upper.
I have a question about the bottom of this. Could you turn over, please?
Yep.
Have you actually inserted one of your real motors into this airframe to be sure that the forward closure will go inside that little cup?
Okay, so we do not have this possibility as we are in Argentina and we are not able to ship motors here due to laws and regulations. But we have continued with the same approach of previous years. This section of the manufacturing process has a slight taper to it that allows for a range of measurement. And we have designed this bulkhead so that
you're flying in 5500, correct?
Yep.
So I have one. I can measure this for you if you want. But I had a team 2 years ago that machined that part slightly too small, and we couldn't insert the motor. So it's very difficult to make that change once you glue this in.
Yeah.
Yeah, sorry, Brent. We did use the drawings sent by IREC to dimension these.
Yeah, but the drawings could be out of date.
Yeah.
You know, guys, you cannot trust the drawings 100%.
I have an old model
sorry.
too, but
Felipe mentioned this. I think it was cut off by the noise, but that section is actually a cone. It's tapered so as to be able to fit a range of diameters, not only the nominal diameter from the drawing.
Brett, if you can send us the exact measurement, set of calipers or micrometers, we would greatly appreciate it to double check our work and make any adjustments needed here.
Yeah.
Does it happen often that measures or the drawings are not up to date from IREC? Or
There's probably 3 or 4 versions of the 5500 drawings on the internet somewhere.
No, it's not from the drawing. I spoke with IREC's salesperson, and they sent the drawing personally to me.
Okay. Well, I'm just saying, if you don't check this, it's nearly impossible to fix this.
I recommend that the Brett says, because I work with international teams that they have the same problems and they come with the competition and they need to make a change for adapt the final parts.
Okay, this is a great recommendation, great information that we're receiving. So thank you, Brett. It would be great for us if you could send us the measurement after the meeting.
And then the other measurement you have to be extremely careful about is the length.
The length, yes.
Yeah, so we achieved
Of the motor.
The length of the motor, yeah.
We have a strategy that has worked for us in the past, in which we glue the center ring at the bottom of the airframe when we already have the motor, so that we can measure it properly, and we let the the epoxy cure for the recommended time, and we have had no problems with that strategy so far.
Can you show us that bottom section, please?
You mean the bottom section where we are going to attach the motor?
Yeah.
You just described it, so I wanted to see how it inserts into the airframe and how you can make in the field adjustments once you get your motor. I just want you to show what you just explained.
Okay, great. So let me show you. I can show it to you through the presentation. The part
But
is
don't you have the parts? Can you show us the parts?
no. The center ring is still being manufactured, but I can show it to you right here.
Okay.
This is the conical centering, and what Pipe was just saying is that we can adjust where we glue it, if it's whether more to the aft end, to the forward end, or to the aft end. So there we can make some field adjustments. Also, the centering is conical, so it can tolerate differences in between nominal measurements or nominal dimensions and deviations from it.
So the cone. So is there any thrust transfer for this? Or
Yes.
is all of the thrust transferred at the forward closure?
No, so the idea is the following, right? We get the motor physically when we are in the US. We insert it into the thrust plate that has that conical part, and we insert it as far as it will go. It accept like it bottoms up with the thrust plate, and then we slide from the top of the motor the tapered centering ring as far as it goes, right? Because the motor has a ledge on the bottom. We insert as far as it goes, and then we glue it at that height. So the motor is now transferring thrust through the thrust plate at the top of the rocket, and also through the taper of the centering ring. Despite from this, we have made all of our calculations, like taking the worst case scenario in which all of the thrust is transferred through the thrust plate.
So let me clarify my understanding of what you just said.
Okay.
The bottom flange of the 05500 case is transferring thrust to an aluminum part at the base of the rocket?
Yeah.
Okay. And that part, is the thrust then transferred through a glue joint, or does that thrust plate rest against the airframe tube?
No, it's transferred through a glue joint and two screws.
So how big is the glue joint?
The glue joint is, I have the measurements in millimeters. I don't know if it's approximately 2.5 inches tall by the full diameter that is 6 inches. So we have, I don't know how much the area is in inches, but we can make the calculations for you.
Yeah, okay.
2.5.
So it's interesting, Walter. Normally I see thrust plates with a mechanical transfer of thrust to the air. I've never actually seen a thrust plate with glue joint.
Especially in a O motor. Okay.
Yeah, it gets hot too. So this area heats up.
If it's better for you guys, we have no restrictions that wouldn't allow us to put screws at that part of the motor.
If you have the possibility to add screws, I recommend that you add.
Or put a flange and have the thrust plate directly transferred to the airframe and leave a little space at the top, so that instead of adjusting the bottom, you have the ability to move the motor against everything, because you don't need that little cup at the top.
Okay. we will look into that and make a more reliable system that leaves you guys.
Yeah, so just my advice. The top motor retention with your radix joint, the tighter you make the tolerances and the less slack you have means if the motor is not quite made to spec, that is, if it doesn't quite match the dimensions that you're given, what you typically have to do is put a small spacer ring at the bottom around the motors so that the thrust is transferred to what you have at the back end, right? You don't want to be doing thrust transfer on an 05500 through the forward closure. It's glued and it's a high failure point. So my advice is don't transfer thrust for this motor through the forward closure. Always in the back. My advice.
Yeah, me too.
We will attempt to make more of the load go through the back centering ring rather than all through the forward closure. Just
I would do 100% of the thrust in the back and 0 in the front. My advice.
Okay. Just as a reassurance, I don't know if there was an understanding gap or we explained something improperly, but this joint right here, it doesn't transfer the thrust through the glued joint, right? This has a ledge here that sits against the tube and transfers the thrust through the ledge. So
I'm worried about the glue failing in the forward closure for the 05500.
Okay. So inside the motor. Okay,
yeah,
perfect.
Yeah, the most likely failure you will have on that motor, it'll KATO by blowing the forward closure out.
Okay, perfect. We will look into that then.
Great.
So I always want the forward closure with a little tension through the screw that's holding the motor in, but not thrust transfer on that metal closure.
Okay, we're looking into that. Okay, yeah, we can do that.
I just think it's going to be safer and better for you.
Okay, yeah, we can do that. We can absolutely do that. Thank you for the advice. We didn't know that it was a common failure of the 0500.
Okay, and other question about the motor retains. Do you use the same part or the lower center ring to retain the motor in place?
If you use with the centering ring, yeah, to fix the motor in place, that's what the tapered surface is for, and that's what allows us to transfer loads from the motor to the airframe. It serves both functions.
So can you expand? Pardon me, I just want to try to understand this rear section better. Do you have an expansion that shows us the parts and how the motor flange interacts with them?
The motor flange interacts. You mean this?
Yeah.
More
expand it more, please, so we can see exactly what's going on here.
Yeah, I have the same recommendation about the upper of the old motor, because if you don't have the physical dimension of that parts, and in the case it doesn't fit, which is the worst scenario that you plan to make the change.
Great. Yeah, we'll take it into account. So this is an expansion of the center ring.
Okay, so that's the centering ring, which is currently you plan to glue that in.
Yeah. Per your recommendation, we will consider joining it with a bolt to both the fin can and to the boat tail.
If it was me, you've got this nice part. I would have that aluminum part have a small flange on it that goes to the diameter of the OD of your airframe. That way, the flange presses against the airframe, and you don't have to worry about failures of screws or glue.
Okay, yeah,
Yeah.
I got you.
That's a great idea. We will look into manufacturing that.
Yeah, that's a classic design for a thrust plate, where you have physical transfer to the airframe.
Okay, yeah, perfect. And
ab-
we can machine spacers to take with us into when we go to the US to adjust that final measurement.
okay, you can tell me more about the bow tail, the material, and this is the final position of the nose of the rocket motor and the nose.
The
Okay.
nozzle is longer than that. The nozzle is really long.
Yeah.
So all the measurements of the motor were taken from the drawing that Aerotech sent us.
Okay, well, that's not an accurate picture of the nozzle. I guarantee you it does not look like that. It's much longer.
Okay, we have some resting material, some resting space, if in case this is longer. So, but we will see it more in detail. We'll.
The nozzle is like this long.
Oh, sorry, I can see you.
So
Brett,
it's
can
like
you
Maybe 4 or 5 inch.
yeah, it's like 5 inches long. It's this big.
Okay. Okay, great. So we'll review this, but the measurements were all taken from. But we'll check this. So if it's longer, we have a mold already made, and we can manufacture the bow tail again in a longer dimension if needed. If the nozzle exceeds the limit, the limit of the bow tail. But we have some field arrangements or some plans that we can, some drawings that we can slightly change so that the bow tail matches the dimension of the nozzle. So people is showing you.
What is the material again?
It's yes.
It's fiberglass.
It's fiberglass. Yes. Felipe is showing you on the other camera the bow tail.
What's the clearance between the fiberglass and the nozzle?
The clearance was around.
What is the?
Let me. The motor is from 98 millimeters outer diameter, and the bow tip is around 130 millimeters diameter. So it has a clearance from approximately 40 millimeters in diameter, which is a little less than 2 inches.
So,
exactly.
So the part you're holding doesn't match the drawing I see on the presentation. It's much longer.
Yeah.
No, actually, you mean the bow tail is longer on the?
That's correct. The bow tail
camera?
that I see in your hand seems longer than what you show in the drawing.
Yeah, it seems longer because the cylindrical part of the bow tail is attached to the center ring. So in the drawing, maybe you're just seeing the conical shape, but here it also has a cylindrical surface. That's why it might seem shorter.
So where does the nozzle end in this boat tail? Is it recessed, or does it come out through the hole?
No, it's recessed. It's recessed so that the bow tail can take the impact at landing.
I don't recommend you do that, but
Yeah.
this is a
recommend
really
that
powerful motor. I wouldn't. let me finish for a second, then Walter, maybe you can jump in. But I might go flush, but I certainly would not recess this nozzle in a boat tail for this rocket.
Why? Why? Just to understand the concept, why wouldn't you recess it?
I guess it goes counter to my my instincts and experience flying big rockets. I normally I'm very careful about recessing motors inside of airframe tubes. I only do it on smaller motors. So I don't know the engineering. So I can only tell you my instincts. I can't tell you why. I just,
Okay, is it because
it worries me.
is it because the boat might burn or because
So I have another
is it because the
team. One of my other teams is flying an O5500 from Brigham Young. They did a test flight. They have a 3D printed boat tail that screws to the thrust plate, and it is flush with the nozzle. In their first flight test, the boat tail deformed because of the heat from the nozzle. And it was a high temperature 3D printed. So they're redoing it. They're putting aluminum tape inside the boat tail to reduce heat transfer. And that boat tail is flush with the nozzle. It doesn't recess the nozzle. There's quite a bit of heat and air disturbance around this nozzle, and it caused heating in a section of the boat tail this big to deform, and the rocket started to do some coning during boost because of that, they think.
Yeah, we have a plan regarding this problem. We have Nomex and Kevlar material here at the university. So that's a material we work with our protection supplier, and it's meant to withstand high temperatures and flames for about 20 seconds, which is pretty much more than what the motor burns for. But it's material meant to withstand high temperature, and that's why we think it wouldn't burn. But if you think that it would be a problem for a rocket, we will consider changing it and putting the nozzle on the outer side of the boat tail. But may I ask if it isn't a bigger problem for the nozzle to impact against ground rather than having the boat tail with some burns?
I've never worried about the nozzle hitting the ground. For me, this is a one-time use motor.
Yeah. Is there that the nozzles have any issue that your rocket pass for the competition?
Yeah, because if you break the rocket airframe, you lose points.
Okay, but the motor doesn't count as a piece that can be destroyed, or if we break a part of the nozzle, it doesn't deduct points.
How heavy is your rocket? This part on descent.
On descent,
yeah,
22 pounds. That's 40 pounds, 45 pounds, something in the realm of that.
So it's 40 pounds coming in at 20 feet a second. Guys, the nozzle on this motor is really strong. So I can't imagine extensive damage to the nozzle. Also, the Your recovery system will cause the airframe will be completely vertical. You're not, unless there's very high wind, you're going to be coming straight down into basically a sandy, kind of limestoney surface, not rocks, at 20 feet a second. I can't imagine extensive damage to a nozzle under those conditions, particularly this motor's nozzle.
Okay, great. Great to have that out of the question. So we'll consider changing that. We'll make the adjustments after the meeting.
Yeah, the biggest risk is if you have high winds, you're going to clip one of your fin tips and break a fin. That's more likely than your nozzle breaking, in my opinion.
Yeah. So if there are no more questions about the centering and the aft end of the motor retention, we are going to present the fins and the fin details. For that, Valentin.
Just to summarize my feelings, and then maybe Walter, you could say it as well. I'm uncomfortable with your boat tail and rear thrust transfer design. So this is one area I'm very uncomfortable about now. So I'd like you guys to think about this and come back with something that's lower risk, stronger, and I'm happy. I'll be in my shop today. I can measure. I have an 5500 sitting there. It may or may not be exactly like yours, but if you want me to measure any dimensions, I can do that for you today. Just send me the list of dimensions that you'd like. Okay.
Great. That's great. Thank you, Brett. So we dimensioned the joint, but we understand your concern and we'll work on it to get a more reliable system. Okay.
Yeah, and stronger. It's. Have you flown a motor like this before?
No, we haven't.
Okay, so be careful.
Yeah, it's a powerful motor.
That's really too much your advice, Brett.
Yeah, and the other thing I'll tell you is, no matter what you think you did, sometimes these motors surprise you. So be really careful and conservative.
Great.
Yeah.
Great. Yeah, we try to be as conservative as possible in design, but these considerations are good to be implemented now. So Walter, yeah, sorry, you were saying?
Yeah, just one more recommendation. In that actual configuration that the rocket nozzle are inside the boat tail, you have aerodynamics vacuum effect, and I recommend that the nozzle of the rocket motor go outside half an inch to prevent that aerodynamic effect. Because do you have a vacuum effect that you need to sorry if my English is not the best one, but
no,
I
it's
recommend
okay.
you
We
that
understand.
the nozzle one.
Yeah, so I second what Walter said. The
Right.
vacuum effect I really worry about, and you should have the nozzle flush or protruding, not recessed.
Yeah.
Okay, great. So do you have any more comments about the motor retention?
No.
No, that's
Great. So we'll move on to the
fins.
Okay, so should I start? Okay, so well, I was in charge with Tomas the dimensioning of the fins. Well, our main challenge was to estimate the in-plane torsional rigidity G of the carbon composite. Due to our lack of testing machinery and our lack of resource in materials, our strategy with the design approach was to rely on theory and estimations of lamination, primarily on using classical lamination theory developed by Jones to build some scripts, mainly in Python, to find the optimal geometry of lamination. I'm talking about ply orientation, ply sequencing, and we try to use best of both worlds when laminating. This particular ply that laminate that we achieved uses both uniaxial ply and biaxial plies that are sequenced we put 1 0-degree laminate ply, and 2 45-degree biaxial ply in order to achieve an optimal value for the bending torsion properties of the fin. So our intention with this analysis was to achieve an accurate G value because according to our studies and estimations, previous years of the competition didn't require to provide an accurate G for the verification of flutter. So our worry was that our whole analysis would be wrong if this particular number was with a considerable offset. Our thickness that was considered optimal for achieving the safety factor of the competition, that was 1.5, was achieved using an 8mm ply or laminate, that has a flutter velocity of 143 meters per second.
1,430 meters per second.
Yeah, sorry. That in our criteria gives a good range of operation for our fins. One consideration that we try to cover also was the tip-to-tip reinforcement that will be applied after we mount the fins. That aspect of the construction was modeled thinking that the fin was already with the thickness provided with the reinforcement. So our expectation is that the final flutter velocity while flying will be higher due to the damping of the final structure of the rocket. So yeah, that's all I have to expose.
Great. So some general properties of the fins. It will feature a 300 millimeter root cord and a 1.1 caliber due to previous suggestions on iterations. So this would ensure that our fins don't lose their ability during supersonic speeds and provide enough root cord to keep them attached to the airframe at every time. So as mentioned in the drawing, the fins will be inserted into the fuselage through the jigs that we showed previously. This aluminum mounting devices that Felipe is showing in the other camera. The jigs will be glued to the airframe, and then holes will be made to that size on the airframe to attach the fins. This will provide higher rigidity than just gluing them to the surface.
How many of them are there?
We have 3 per fin. And we estimated through calculations that that's almost the same as fixing the entire root cord, but allows us to gain approximately 800 feet of height due to mass reduction. But
Where will
provides
the-
the same.
Where will the screws be located in that bracket?
No, it's glued to the airframe. And we put those joints, those glued joints, according to the testing we did of lap shear joints.
Will you have internal fillets?
Yes, we will
Yeah.
have internal fillets for the jigs. The jigs also will be glued with carbon fiber to the airframe, and we will have also a tip-to-tip on the outer side. Also, the radius at the outer side between the fins and the airframe. And well, that would be it. We would be using 5 layers of carbon fiber for the tip-to-tip.
What is the diameter of the fillet inside and outside?
Diameter of the fillet inside and outside, it's around 15 millimeters. It's what we're thinking of doing, just to provide rigidity in the union.
Have you used this technique before on any other rockets?
Which one?
These brackets and the internal fillets.
Until now, we've used the gluing of the fins directly to the rocket and then do a tip-to-tip. What we think of this technique is that it should improve, provide at least the same bonding capabilities of the glue joint, and improve them based on the fact that they will be joined to a more rigid structure. So they should at least provide as the previous fixing method.
Okay, so you've not used it before.
No. Since we don't have the ability to fly in Argentina with big motors, we're testing it now.
So are you going to glue the brackets to the airframe first, then the fins in? What assembly sequence will you use?
First, we will do the holes on the fin can with a jig
slots.
that aligns. Yeah, the slots with 3D printed jigs that align the slots with the actual direction of the rocket. Then we'll glue these jigs to the holes, to the slots we make, and then we'll fix the joints with carbon fiber to the inner side of the rocket. Then we'll do the inner gluing of the fins to the jigs. Then we'll do the outer epoxy radius, and then we're going to do the tip-to-tip on that sequence.
Nice.
Thank you.
How long will this take you?
Oh, the sequence?
Yeah, it's a lot of work.
No, an afternoon at most. We've done all of the first sequence. I mean, it will take 2 days. One for bonding the jigs, because we already have the 3D printed devices to make the holes, and 1 day for doing the slots and to glue the joints, and another day which is planned to stick to, well, let that glue dry, and then to stick the fins into the jigs and to make the epoxy bonds.
What kind of epoxy do you use, and what's your cure time?
We use epoxy EA 100 HP from Loctite, and our curing time is from 1 day approximately.
That's 120 HP.
120 HP.
Yeah, so if you're going to do fillets that require 1 day to cure, it's going to take you 4 days to put the fillets on the outside and inside, right?
Why? On the inside,
Well,
we plan on doing them on the
maybe
using
you do it differently, but,
3D
I was just saying that normally if I have a fillet epoxy laid out, if you turn the rocket 180 degrees, the epoxy will drip down. So you have to wait for it to cure. I'm sure you know how to do this.
We're planning not
Yeah.
on doing it horizontally, but doing it vertically, so it drips in one direction instead of to the sides. So we would be able to glue all of the fins the same day, and that would be our idea. Not do it 1 day at a time.
So the radius of the fillet is, you said 15 centimeters, or is it 7 centimeters?
No,
So-
it's
so
7.5.
What I mean by radius is if this is the fin, like what's the radius of the circle that you would draw between the fin and the airframe?
You mean if these are the two fins, what would be the diameter of the fillet? The diameter would be from
The epoxy is laying in kind of a
Yes,
circular
yes.
shape. What's the radius of that circle? Walter asked this earlier. I thought you said 15 centimeters.
You mean the radius or the diameter? The
Either
radius.
one.
Yeah.
Either one.
Oh, okay. So the radius. Let me check. No, the diameter is from 15 millimeters, not centimeters. Right?
Yeah.
That's very different.
That's a little more than half, a little less than half an inch.
Sorry, did I say centimeters previously?
Yeah. You
Oh,
did.
sorry.
Hmm.
Sorry.
So how are you going to get that much epoxy to stay in the joint if you hold it vertical? It doesn't seem logical to me.
We have another epoxy that we are going to use for the fillets that has aluminum powder, so it's more rigid, it stays in position, it's higher in density. It's not the usual epoxy glue. It has some added substrates that make it more rigid. It's not like a liquid, but it's rather something like more plastic.
Like peanut butter.
Like peanut, yeah, exactly. It's like peanut butter. It has that kind of consistency, and that's
Okay.
what we're using for the fillets. Sorry if I wasn't clear on that.
So you're going to glue them vertically and let the epoxy drip down, and then you're going to apply fillets with a very thick paste filler, and you're going to keep it vertical, not horizontal.
Yes, that's the plan.
I've never done that before. I've never seen fins put on vertically and filleted. So,
We'll send you the video.
yeah, I trust you, but with the epoxies and fillers that I use, it's not possible to do that reliably.
I think this epoxy bond is special from Argentina. It's called Airpox because it has this aluminum powder.
Okay.
But we've done it last year like this, so I can assure you that this works.
Sweet. All right.
Yeah, the situation with this case is the motor that you will use in this competition. I wanna show you a photo that a previous team in 3 years ago, exactly with the same motor, and this is what happened with the fins. They have a fileter in the flights,
Sorry, that's
and
blurry. You. Oh, right there. That's better. Great.
yeah, let me show you what happened. They make a tip-to-tip, and they make with fiber, the carbon fiber. But let me show you another video. And I think that the bread phase is, I recommend that you need take the enough time to attach the fins to your rocket to prevent that tin of case in your flight.
What do you think happened in that case?
The tip to tip and the assemble in the fins of the iframes is not the best one.
Okay.
And with the velocity that motor gives you of the rocket, just take out the fins.
Yeah, my Brigham Young University team did their test flight for this year, and the rocket went slightly unstable during boost, and it tore the fins and the tip to tip off. It like peeled it off as if it was never there.
Yeah,
Interesting.
that's
It's exactly the same failure that Walter just showed.
We'll be careful to sand everything down to get a proper joint, and then respect the curing time and have a procedure as clean as possible, so that our joint is resistant.
As strong as possible.
Yeah,
yeah.
take care of
What-
that.
What sequence do you use to prep your fiberglass before epoxying? What do you do?
Before epoxying you
Yeah.
mean you said the fiberglass.
Yeah, let's say you're gluing one of these fins into that bracket. How do you prep the material? You do.
When by prepping the material, we sand it in the tangent direction of the force we expect. So we create this.
So just to
Nothing-
summarize, just
Yeah.
real quick. So you sand first, then you clean it somehow?
Yeah, we sand it first, then we clean it with isopropylic alcohol. Then we wait for it to dry. Then we start the procedure to bond the fins. And
My personal recommendation, and Walter has his own opinion, he can say too, I would clean with a fresh rag and acetone before you sand, so that you don't accidentally sand any mold release into the fiberglass. Then I would sand in all four directions. So this way, this way, this way, this way. Typically 150 to 220. Then wipe again with acetone, again with clean rags, and then glue immediately. So I recommend a procedure kind of like that.
yeah, that's almost the procedure we used for the lab shear test, where we tested all of these joints between aluminum and fiberglass. But we, instead of sanding in every direction, we just sand in the directions of the tension applied, because that's what we found to be optimal in terms of resistance. But we'll check that also.
Yeah, it's the best way that you attach the fins to the iframe.
Yeah, I see a resemblance between the acetone and the isopropylic alcohol. So yeah, I think the method is quite similar, both the one you are using and ours.
Yeah, I
So-
typically use acetone or mineral spirits. I don't use alcohol for cleaning for epoxy. So, you know,
Yeah, that's what we wait for it to dry up. But well, we'll also consult with our expert if acetone works and if it works better than our cleaning substance. Great. We have it noted. So that would be the end of our presentation. If you have any more questions, we're glad to answer them.
Yeah, I just wanna see the avionics bay again.
Yes.
Just I wanna see the attachment of the flight computers, the batteries. I wanna see the cables.
battery mounting, you know, see the details of that.
Yeah. They're just demounting the radix joint, and they'll show you right away the connections of the avionics bay.
Do you guys have your rail buttons? Can you show those while they're doing the av bay?
Yeah, they are at the shop. Let me just send someone to look after them, and we'll have them right away.
And just while you're disassembling and doing Walter's AV bay, how will you mount the rail buttons?
Just give me a second. En la caja de los we will mount one of the rail buttons at the aft end of the motor in the centering ring, and the other one goes bolted to the forward thrust plate of the motor. So they are really, in both cases, we're going to use epoxy to make a fillet so that the joint is more resistant.
But you have a screw that is tapped into a hole in the aluminum. Is that correct?
Yes.
Okay.
All right. Thank you.
Okay, so we are ready to show you the.
Here they are. So these. Oh, great.
We can
These
open them for you.
are our rail buttons.
We have the aerodynamic version.
We put them at apogee,
Yeah.
and this is the screw. These are the screws we would be using.
Okay, great. Thank you.
We're ready to show you the electronic bay. What in particular did you want us to show you?
I just wanna see the attachment of the batteries and the flight computers, and if I wanna see if the flight computers are into the surface or they have a space between the surface and the flight computer.
Okay, great.
Which surface? The upper or lower or both?
Between the surface that are mounting.
Turn it
you mean
sideways so we can
the
see.
3D structure. Yeah, it has a space. It has a gap, and it's joined to the 3D structure by separators printed into the 3D structure and bolts. But it's
Okay.
separated from the 3D printed structure.
This is to ensure that the bar meter is sensing accurately.
Okay, and the vent holes for that avionics are at the sides of the flight computers?
That's right. Yeah, that's right.
Okay. Okay. Perfect. Okay.
You have a telemega, is that right?
Yeah, that's in the telemetry bay in the upper side of the rocket. It's just for data acquisition and sending the data to the ground station.
All right, so you're only using it for GPS.
Yeah,
Yes, basically. And to extract data, flight data at touchdown. By
And then
removing
you have the featherweight is in the av bay, right?
yes.
So the battery, retention, it looks like there's a piece of plastic on the aft side. Is that correct?
Yeah, here. Yeah, it has at the both sides plastic supports with screws.
Are the wires soldered to the battery or are there contacts there?
Soldered. Soldered.
Okay. And could that plastic break at the bottom?
Oh no, it weighs about 15 grams, the battery. So at max G does not affect the support.
I recommend you that maybe change the lower plastic part with another big one that can support with the aluminum plate.
Here.
Yeah, a bit. It's better that have the aluminum plate to support the battery than only a screw.
Okay, great. Yeah, actually, we dimensioned the joint to withstand the forces, but we can do that modification.
Okay. Can you rotate the avionics bay to see the other side? Okay.
Oh yeah, of course.
Okay.
Can you show it closer to the camera, Pipe, please?
Yeah, the other batteries are inside.
Yeah.
or
Yes.
is- Okay.
And they are sealed. They have their own battery cases, and those are sealed with zippers.
Okay, that's battery are fine with the location. Okay.
What kind of wire are you using?
The size of the wire,
Is it stranded, solid? Do you tin the connections before you put them in
Yeah.
the connector? You use ferrules? What about the wire?
the wire is a multi-wire one, like
Yeah.
3-watt.
Stranded?
And
Okay.
yeah, all the connections are bonded by soldering paste and tin.
Okay, nice. How do you pass the wires to the top of the Raptors?
Yeah, so we have a little space between the joint and the coupling side aluminum. So we cross the 4 wires, sorry, the 8 wires to the upper side by that space.
And then we seal the joint after passing the wires, so that no air can pass back to the avionics bay.
How do you seal it?
We were planning to seal it either with like a putty that came in the kit with the Raptors, or silicone paste and let it cure.
Yeah, I think poster tack is fine if you put a big amount in and really push it down.
Okay.
Yeah, just be sure that the way that you used to seal it replicate to the
Perfect.
launch date.
Perfect.
Yes, we're going to perform the pop test with these characteristics. So we ensure that our simulation matches the conditions at launch day.
Will you use dual match charge cups?
Yep.
And how will you wire them to the altimeters?
It's a simple connection. We have the 8 wires coming from the altimeters, and we basically solder them, and we put a, how would you say, thermal
Joint?
No, el termocontrol. It's a kind of plastic that with heat, it
Heat shrinks.
Heat
Okay.
shrink. I get it. So if the one Raptor is number 1 and the second Raptor is number 2, and flight computers are 1 and 2, which matches go to which flight computers?
one to one and two. I don't get the question. We have the both systems.
So there are 2 matches in Raptor 1, for example.
Yeah, both of them.
So E-match 1 in Raptor 1 goes to flight computer 1, And then the second match goes to flight computer 2, correct?
No, both go to flight computer 1.
So why would you do it that way? Why not change it?
And you have a backup.
Yeah. I strongly recommend you have each flight computer going to each of the 2 Raptors so you have double redundancy.
Yeah. Actually, it's the object to have 2 flight computers in the rocket.
Yeah.
But that doesn't activate the both Raptors at the same time with the first deploy.
You can put a delay in and use a delay in the second channel for your flight
Oh.
computer.
We're doing that at the second altimeter, but having both Raptors with 2 images doesn't activate the both at the same time with one rogue deploy.
So how many channels do you have in each flight computer? How many?
One rogue and one main.
So you only have 2 channels in each flight computer, or do you have 4?
No,
2.
Ah, okay.
Yeah.
I thought you were using the Telemeg. It has 4 channels. You can use them all.
we are using RRC3 flight computers. That's why.
Okay. So you're going to do matches in parallel then? You're going to do 2 in parallel?
Yep. If we were to wire them, how you suggested, then we would have that problem. We would fire both Raptors at the same time.
Yeah. Sorry, I've never flown RC3.
So we're using this because we have tested in 3 flights before.
Yeah.
So we're pretty
It's
sure.
That's what we are familiar with. But
Okay.
okay. Do you have any further questions?
Just to confirm that you plan to put the team name, the team frequency in the rocket when you finish and paint the rocket. And the last question is about the igniter with your own motor. Do you plan to use only the IREC igniter, or do you plan to use another one with that?
We were planning to use the provided Aerotech igniter, but do you see any issues with that?
Yes, I wouldn't do
Yeah.
that.
Okay. We have no experience with O motors, so any recommendations are more than welcome.
I recommend you use the Wildman dual head igniters and make sure that you have a long enough stick. You need an 1/8 inch dowel, so you extend the stick down to, like 50 inches.
Okay, yeah, perfect. We will do that then.
Walter, are you okay with that?
Yeah, I make the same recommendation. After you go to the launch pads, you prepare the igniter with the stick.
Perfect. Great. Great.
Okay. In your opinion, how much percent of the rocket do you think that you need to finish?
How much percent of the rocket do we think? We have metrics of completude of the rocket, and our metrics say that we are 10% away from finishing the rocket ready for launch date. 10% having into account painting and all the final preparations for the safety review.
Okay. I think so.
I don't believe you. I don't believe
Yeah.
you have a lot of work to do.
Yeah, we have a lot of work to do. We are judging it in completeness of tasks. We have already accomplished a lot, but not in time.
If you think about hours, I think you have a lot of hours left.
Yeah, we have a lot of hours left, definitely.
I recommend you that finish all your project in your place and don't come with any work to the competition. I have a lot of experience with the international teams that they have problem issues, and it's more difficult to finish the rocket in Midland without the space of the tools that you need to find.
Perfect.
Yes.
We are definitely pushing hard toward completion.
Okay. Okay. Perfect, guys. Well, for me, I think so. I have all the question. I make a document. I send you an email with the document and all the observation, and I send a copy with ESRA, and I wait for the information of the recovery system that you need to update.
Perfect.
Great.
Do your team have any question about the competition? You already have the law, I don't know, Airbnb, the travel logistics.
We have all the travel logistics solved. We have a question regarding how the ground operations change in 30K COTS. Last year we competed at 10K COTS, and we just wanted to know what differences are there on pad if the
No are difference.
no difference.
I think maybe the only difference is that you use the last path of the range for any issues. But no, do you need to have any other preparations? I don't know if you already have the information, but I think so this year the competition stops at I think so half of the day for the Da Vinci problems because I think so we don't have Da Vinci communication this year, and we start launches from the sunrise to the maybe half of the day, and we stopped the launches and we left the recovery teams to find the rocket.
So, you have only half a day of launches.
I is the information that I have, but I need to wait ESRA that communicate the teams.
Okay. Do you know any other failure mechanisms of the 5500 that can help us at preventing them, either at arming it or other recommendations about the motor?
You need to prepare the motor maybe the first day that you arrive to the competition. Do you need to wait 24 hours to cure the epoxy?
Great. We've seen some KTOs last year.
Yeah, a lot.
A lot of the motor KTOs. Do you know what that happened?
Mainly the forward closure.
Yeah.
Okay, great.
I think it was like 20% failure of the forward closure.
Was the failure due to compression, or was it due to gluing problems or some of that kind?
I don't know the root cause, but probably the teams didn't follow the procedures well.
Yes.
And they didn't wait long enough for curing. Sometimes they don't mix the epoxy sufficiently. So I recommend continuing on Walter's recommendation that probably Wildman and Aerotech will have motor assembly sessions like they did last year. Sign up for the earliest one you can. You need to glue the grains, wait 24 hours, then glue the closure and wait 24 more hours. So to safely fly that motor, you need 48 hours.
Perfect. Great.
And you need really clean conditions, and you need to follow. So I can help you if you have a place where you think you could do this yourselves. I've done this motor 4 times already myself. But if you go to the motor assembly sessions, you can have Aerotech helping you, which is good.
Yeah.
But remember, it's overnight for grains and then overnight for closure. So you need 2 full days.
Perfect. Great. That's all on our end then. If you have no further questions, we want to thank you very much for your time and for reviewing our rocket.
Yeah, nice job, guys. Lots of good, hard questions. Walter, I appreciate helping my team here.
Yeah, no problem, but okay. Good luck with the rest of the work that you need to do in the rocket. If you need other recommendation or any additional comments to solve, you send me a message and email. I can respond you. And I see you in the competition.
Yeah.
Perfect. Great.
Okay.
Thank you, Walter. Thank you, Brad. Thank you, Patricio.
Thanks,
Uh,
guys.
Thank you.
Thank you very much.
Walter, sorry, can you send us the link to the recording, please?
Yeah, sure. I just end the link of the recording, and I can send you a copy of the record.
Great. Thank you, Walter.
Goodbye.
Goodbye.
Walter, are
Okay.
you going to send the recording to ESRA, or does the team do that? Which
The team needs to send the record to ESRA. Yeah,
Okay.
don't forget that.
All right.
Okay.
Great. Do we send